Hello. A second. Set up everything. Do I do? Okay. Today we're gonna learn something really important. But while we are waiting, where's my phone? The meaning of life. Actually, that's actually close. That's actually very close. Let me find my thing. Actually, this is it's not wrong though. What you said. And that is splendid. That's better. Okay, let's grab notebook number 5, exercise 5 on from our usual place, GitHub. This one. GitHub. Number 5, exercise. Okay, while we are waiting, I want to know one thing. So someone asked me on the Discord when is the midterm. So this is what I want to know from you. When are your midterms? Because I know you have Algo and SysSkill, like most of you have this, right? System skill. When are the midterm for these two classes? So, so I try to avoid it to make sure that they are not on the same week. Like if 3 of them are on the same week, then you're screwed. When are the midterms for these two classes, guys? Or some other class that you're taking and it's like really hard. Or you guys are not taking no midterm. Did I screw up my phone? Just screw up my phone. Oh, I did not. Everything next week. Okay. So how about midterm gonna be next week? Gonna be fair to you guys, right? Because I was deciding whether it's gonna be next week or next week. Because our goal is hard. I would fail if I take the class. Midterm gonna be, I propose next week then. So this is next week. How about system skill though? Is there a midterm? What's the skill? Wait, on the same day as algo? That means like half of you are dead. Oh, okay. Well, I'll go quiz like every time. And what else are you guys like mostly taking together? What else are there that is hard? So, so I'll propose something like this. It's gonna be next week, but we're gonna have class that week though. Anyway, we're gonna have class that week. It's like a homework. So this thing gonna homework 1 to 4. Please do it. Okay, this thing cover homework 1 to 4. So unless there are like other objection, midterm gonna be next week, which is, let me find the date. The week of, wait, which week is this week? 20. So next week. So it's gonna be week of Monday 1st November. Gonna be week of 1st November to what, 5th November, or actually let's make it till Sunday 7th November. Okay, midterm gonna be posted on this day. This is when you hand it in. Find 2 hours to do it. That sounds fair, right? Like I said, I trust you guys not to do something like stupid. So please don't do something stupid. Okay. Yeah. And it's open book, open note. It's not open your friend though. Just make sure that whatever you write, you learn it. Okay. The homework are going to be no, not the homework. The midterm are going to be close to the exercise. So if you do the exercise, you do the homework, you should be fine. Okay. I'm not going to test you on like something extremely hard. There are going to be some creative problem though. So next week is 3rd October. You actually have the whole week. You actually have the whole week to do it. We're gonna have class on the 3rd of October, but you have the whole week to do the midterm. Even better, right? You have the whole week to do the midterm. But if you know what to do, you should be able to finish in 2 to 3 hours. But take as long as you need. Okay. Take as long as you need. Okay. Any questions about the midterm though? So the midterm is gonna be next week. It's gonna be week of 1 to 7 November, the 1st to the 7th November. Okay. It's gonna cover homework 1 to 4. So that means this thing that we're gonna learn today not gonna be on the midterm, not on midterm. But if you want to use it, I'm fine. Not on midterm. But if you want to use it and it solves your problem, I'm fine with that as well. Because what we're gonna learn today is a really powerful technique. Like Parin or someone said, is the meaning of life ish. Okay, any questions regarding the midterm though? Any question regarding the midterm? Gonna cover homework 1 to 4 and also this exercise still match. So it's exercise 1 to 4. And let me get rid of this real quick and open it again. If you have an iPad, I don't know if you are having the same problem. It's quite lacking after the iPad OS update. It's very lacking for me. And I need to reopen the application and so on. Okay. Any question? Any question? Any questions? Did I screw up the screen? Wait, I think I did screw up the screen. That's why you probably never seen the screen update. Okay, so sorry about that. Okay, the midterm is going to be next week. Cover exercise 1 to 4, which is homework 1 to 4. It's going to be very close to the exercise on the homework. There are going to be the easy one where you can essentially copy things from the exercise and then it's going to work. Change like 2 lines and it's going to work. And there's going to be something really hard that you're going to need to take to think about it. Okay. And the midterm is going to be on the week of the 1st November to 7. I'm going to try to post it on the 1st November and you have a week to do it. So you hand it on Sunday midnight. If you know what to do, it should take you 2 hours. Or 3 at most, or 3. Okay, so let's learn what it is that I really want to teach you today. By the way, this is not on midterm, but if you use it on the midterm, then I'm fine, I'm good. As long as it's a valid solution, then I'm good. Yes, you have a week to do the midterm, but it should take you 2 to 3 hours, but it's your job to find the 2 to 3 hours that you're good. It's open book, open notes, open internet, open Wolfram Alpha, but just don't discuss it with your friend. That's all I ask. Okay, don't discuss it with anyone. If you try to ask the question, ask it on the Discord. Discord is really quiet. You should send the meme or the joke or anything. You should look at the other class. You should look at the other class. They send joke every day. Okay, so today we are going to learn one class of optimization. Okay, so essentially we're going to learn optimization. Okay, but today is like the simplest version, which is like essentially everything. The simplest version, but essentially is everything. It's called gradient descent. Okay. So pay attention though. This is one of the most important topics, which is like the meaning of life. Because if you think about it, every problem you can phrase it as an optimization problem. So for example, you can ask you, let's think about this. Last time we learned how to get the computer to solve the equation, right? So for example, if you want to solve e to the x minus x, okay, wait, e to the x equal to x, right? Then can anyone tell me, can anyone phrase this as an optimization problem though? Let me give you an example optimization problem. So for example, optimization problem is something along the line. Let's say you have an equation f of x, okay? And you want to find f of x is x minus 2 square, okay? Plus 1 maybe. And then optimization problem is the question of find x such that f of x is minimized. Okay, or if you try to be fancy, this is how to write it. It's called arg min. Somehow I just write min, but I really meant arg min of x. That means this is the variable you change. Okay, arg min of f of x. Okay, which means variable to change. So we want to find the value of x such that when you plug this thing here into f of x is minimized. Okay, so this thing gives the argument that minimize f of x. So for example, this thing here is 2, right? Because x minus 2 squared plus 1 is minimized, is minimum at x equal to 2, because you cannot get the first one lower than 0. Right, the first term, when x is 0, then this thing is 1. Okay, but this argmin returns 2 because this is the value of x. Okay, is everyone clear though? Is everyone clear? Okay, this is what I meant by optimization problem. Find the parameters that makes your function. This has a name. This is called the objective function. Sometimes called a target function, objective function, whatever it is, depending on the field. Objective function. Okay, any questions so far? Any questions so far about, okay, this is an optimization problem. And I claim every single problem is an optimization problem, which, think about this. Okay, if no question, think about this. Let's say if I want to solve this. Let's say here's the question. I want to solve this. Can anyone tell me though, can I write this question, right? Solve e to the x equal to x. Can I write this problem as an optimization problem? Which mean, is it argmin or argmax of something? Right? That means it's phi next. Can anyone tell me though? How do you write this thing as an optimization problem? Anyone? Right? So that means you kind of need to find what you need to do. Use a block? Not really. Log doesn't help, right? You want some function that you evaluate it and it gives you equals to number. Very close, very close. But remember f of x, right? F of x need to be something that when you put in the number, right? That when you put in the number and it should give you some quality, right? And then you try to minimize that quality. You guys are really close, Van and Adil. You guys are really close. It should not be an equation, right? It should not be an equation. Okay. It should be just an expression, right? It should be just the right-hand side, the thing that we typically write. What do you think? Can you turn this problem into optimization problem? You don't have to solve it though. If you phrase it as an optimization problem, then I'm good. What do you think? So for example, let me try to take Van and Adil idea. Okay. Let me try to take everyone idea and put it here. Okay. So let's say if I do this, if I say that, okay, the optimization problem that's gonna solve this problem that we have is the following: e to the x minus x, because everyone kind of said that, right? What's the problem though? What value of x that give it the minimum? Right? Think about it. Think about it. If you try to e to the x minus x, right? Then it grows like this. It looks like this. It doesn't really have a minimum, right? So can someone tell me how to fix it? Something really simple. Something really simple to fix it. E to the x over x minus 1. It still has the same problem, right? It still has the same problem. We want to make sure that this function over here, we want to make sure that f of x here is minimized when our condition is satisfied, when e to the x is equal to x. What function does that though? Can anyone tell me? What function does exactly that? What function minimize when e to the x is equal to x? Something really simple, and it looks really close to what you told me. When they are equal, we want it to be minimized. So what should you do? What should you do? What should you do? I could spoil it, but you're gonna be mad at yourself. What should you do? Let me give you a hint. What should I do next? Adil, tell me. Now you see it, right? No, remember, we are not trying to solve, minimize doesn't mean that it has to be equal to 0, right? So for example, last time, f of x when it's minimized is 1. We are not trying to make it equal to 0. All power 0. No, we are not trying to make it equal to 0. We are trying to minimize it. It could be any number we like, right? So think about it. If your function, if your objective looks something like this, and this happened to be exactly the place where x is equal to e to the x, then we're good, right? What can I do about it? What do I do to make sure that this happens? We want something like this, right? That the minimum happens at x equal to e to the x. I give you a hint already. I should write something here. Can anyone tell me? I should write something there. Very good, Adil. Right? You just square it because I know if they are equal, this thing is 0, and because it's a square of something, you cannot go below 0, right? And if x and y, if e to the x and x are not equal, then you get some number square. It's going to be larger than 0 anyway. So yes, you can transform it into optimization problem. Okay, so far so good. So far so good. So I claim like everything we know is actually optimization problem, or even the linear regression last time that we learned. Even linear regression last time that we learned. Okay, let me show you how powerful. If you know how to solve optimization problem, you know how to solve every problem in the world. You could end the world hunger. That's actually a true statement. Actually a true statement. Argument. What about if last time, right? We tried to do this. Oops. We try to fit a line to the points. This is what we did last time, the last 2 weeks. Okay. So the problem here is that we are trying to find M and C, right? Arc min, and we adjust M and C. You can adjust any number of parameters you like, M and C. And the cost function that you remember last time, it was mx plus c minus mxi minus yi square, right? So what it says is the following, if you still remember from last time. We adjust the slope and intercept such that the distance from the line to the point is minimized. Okay. Or even this problem, what should you eat for lunch? Okay. So even the problem of what should you eat for lunch, right? So in your mind, you have some objective, right? So you're gonna be, okay, minimize, say arc min f in the set of all the food, right? For some food, and then your cost function is gonna be, okay, maybe the price of that food, right? And maybe the time it takes to eat it, right? The effort of the food. If you can quantify it, then you're done, right? If you can quantify it, you're done. Or maybe something about your preference, right? If you can quantify, so essentially all I'm writing here, oops, all I'm writing here is essentially your preference for the food. Okay, so Pascal, I show you that optimization, knowing how to solve optimization problem is very powerful. But what we are going to learn today, you can see that there's some difference between what I talk about here and what I talk about here, such that, okay, today what we're going to learn is we're going to learn what if x is in real number, right? You have some continuous value because food is discrete, right? You pick common guy, you pick noodles and so on, right? So discrete optimization is a much harder problem, which you're going to learn in algo. Like, I'm not sure if you learned it already. So for example, the shortest path and so on, right? Is essentially discrete optimization. Yeah. Right. So that's the difference. What we're going to focus today is this guy. we are going to touch on some of this maybe next month or something. Next month, later on next month. Okay, we're going to touch on this. Okay, so some of the method that you learn how to solve in Algo, you can actually write it in like 3 lines, except your big O is going to be terrible, but it's going to solve it. Your big O is going to be terrible, but you're going to solve it. Okay, so far so good. So one thing you learned that a lot of problem, actually every problem, if you can formulate into optimization problem, then you're good. Okay, but the formulation is typically the hard part. But what we're going to learn today is if you have the optimization problem already, how would you find the answer? Okay, before we go on, I want to show you one thing before we scream to each other. Achan, what about the other one? Okay, let's say if I know how to minimize any function, assume, which we're going to learn. Assume we know how to minimize. Okay. Then you may ask, Ajahn, what about maximize? Because typically I want to maximize the profit, right? What about maximize? What about argmax? Okay. Remember, argmax means it's the value of x. Remember, it's the value of x. Value of x that give maximum f. Okay. So let's say we know how to find argmin of anything, right? We essentially we know how to find argmin of everything. The question here is, do we know how to maximize? Okay. Or in other words, can you write this as argmin? What do you do? What do you do? Very good. Just put the negative, right? Just put negative. So that means optimization is minimization because every single package you're going to use for the rest of your life, you're going to write your own today, but you're going to use the package for the rest of your life, right? That minimization is essentially maximize. If you know how to minimize, you know how to maximize. And if you want to see this as a picture, because I think some of you still get confused. So for example, the argument that make f maximum, f looks like this, right? Is here. If I flip f of x, right? If I flip f of x, let's say I flip it here, right? The minimum minus of f, right? The minimum is exactly the same place as the maximum. Because when you negative the boss number, you get the least number. Okay. Any questions so far though? And any questions so far though? Any questions so far? This is a very important point. So what we're going to talk today, we are going to only talk about minimization, but essentially we are talking about maximization as well. You just put a negative sign. Okay. The next thing that I want to talk about before we get into how to do this. What if? What do we know about this? Argmin of f x, let's say f of x plus 10. What do we know about it? Let's say add a constant to a function. What happens to it? What happens to the argmin? Right? When I add a constant, what happens to the graph is that it's going to shift up, right? What happens to the minimum? What happened to the place, right? Remember, this is the place where the minimum occur, not the y value. What do we know about argmin of fx plus 10? Right. Minimum are going to be happen at exactly the same place, right? Remember, argmin is the place where the minimum happens, not the value of the minimum itself. Yes, what Saran said is exactly right. That the minimum value are going to be different, but the place where the minimum occur is exactly the same. So sometimes if you write it like this, then you just cut off all the constant. It doesn't do anything. Okay, so far so good. Okay. Any questions so far though? Any questions so far? Okay. So we learned a couple of things that every problem you can write as an optimization problem, right? As long and if you learn how to minimize, you learn how to maximize, and you can ignore the constant. Any other questions so far though? I think this still very simple, right? Any question? How to optimize learning? Right. Let's try that. How to optimize learning. What would you do? Okay. Actually, that's a good question. That's a good question. What would you do? That's exactly how we would approach the problem. So let's think about this. Saran suggests something really interesting. How would you optimize learning? Let's say you want. Let me try to ask something more specific. Okay. Let me try to ask something more specific. Let's say you want to find the best time to wake up to optimize your learning. The best time to wake up. Okay. So the best time to wake up. So this is time to wake up. Let's say you can test it like many times. Let's assume you can test it many times, right? And then this is like your learning score. I would love to say the grade, but the grade again is not learning score. Grade is something really stupid that university forced me to do. It doesn't measure your intelligence nor anything. Okay. Because I know a lot of smart people, they're like, I don't know if you know Peter. Way back then, there was a student named Peter. He is really smart, except when he did my test. So okay, let me talk about the midterm. Midterm gonna have like the easy part, which I made sure that everyone passed the course because I hate grading, right? And then there's a hard part, and there's a guy named Peter. Most people are gonna do this, right? Gonna do like all the easy and maybe some of the hard. And there's a guy named Peter. He said, easy doesn't give me enough challenge. I don't care about the grade. So I'm just going to do this. And I'm just going to ignore this. And I'm like, come on. So please don't do this. Please don't do this. Please don't do this. And that's why I say grade is not a real measure of your intelligence. Grade is a really stupid metric. Okay, it's a learning score, right? So let's say you try today. 8 a.m. You get some score. Okay, let's say this is 8 a.m. I'm pretty sure none of you programmer wake up at 8 a.m. unless you have like easy class or whatnot. You're forced to. Which class is 8 a.m.? ODE class. Oh, math people wake up so early. I don't know why. Math people wake up so early. Okay, so let's say you try today 8 a.m. Okay, so what would you do to find the best spot? What would you do to find the best spot to wake up? Let me put minus learning score as well because you want to minimize it. Let's say you want to minimize it. Okay, so function you want to minimize. Okay, function you want to minimize f. You want to minimize. What would you do the next day? What would you do the next day? What would you do the next day? What do you think? Wake up at 9. Good, right? You want to like move a little bit, right? You move a little bit at 9 a.m. So this is the second day. Okay, you see, it's better, right? You see, it's better. Okay, actually, let me write something more physical. Let's say it's dizziness in class. You want to be like at least dizzy as possible, right? Okay, given this, what day would you try 10 a.m. or would you try 11? No. Would you try 7 or would you try 10? What do you think? Given this, 7 or 10? Why is it risky? Why is it 10 a.m.? Why is it 10 a.m.? because there's some sort of trend, right? This is a key idea. This is a key idea. This is a key idea. There's some sort of trend here, right? You can sort of draw a slope here, right? And then you follow your new guess should follow the trend. So far so good. So the key idea here is the following: you have a solution, you make a new guess, and this thing is hopefully a better solution. Just like what you did with Newton's method, right? You have to guess a solution. The two are actually really close. The two actually, the optimization and Newton's method are actually really close. You can formulate one in terms of another, but it's a new guess that you hope is better. And if you keep doing this for a while, right? If you keep doing this, keep guessing, you guess it's the solution, and then you improve the solution over the time, you should get the best solution, right? Then solution, better solution as we put more effort. Okay, so far so good. So far so good. So that means the goal that we need to figure out is how to improve the solution. Okay, and Risky suggests something that Ajahn is easy. You just look at the trend and then you know where to go, right? You just look at the trend. So let me clean this thing up. Let me clean this thing up and make it sounds like more math. Okay, so if this is f and this is x and the function looks like this. Okay, remember you try one point at a time. You don't know the whole curve. Let's pretend you don't know the green. Let's pretend you don't know the green. But if the starting point is here, okay, if the starting point is here, you can look at the trend, right? Because you know how to take the derivative. You know how to take the derivative numerically. Okay, so the derivative will look like this at this point. So far so good. The derivative looks like that. So which means, is the derivative here positive or negative though? Can someone tell me? Derivative over there, is it positive or negative? You learn math, right? Negative, right? This thing is negative. And given the point and the slope, which way would you want to go? From x, would you want to go right or left for your next guess? You want to go right, right? So think about this. You want to walk. If you want to go right, it means your x would increase, right? So that means your solution, the improvement, right? The new guess, x new. Okay, some people call xn plus one. Let's call it xn plus one, right? It should be your old guess, right? This is new guess. This is the old guess, right? Plus, right? The step size. I think this one is clear, right? Multiplied by the correct direction, right? The correct direction, we determine it from the sign of the slope. If it's negative, you want to go positive and so on. So essentially this thing adds a minus and then the sign of the slope, which is, let me write it like this. Let me do this. F prime of x over absolute F prime of x. Okay, this thing is the sign. Okay. Is someone so far so good? Your intuition when you write it as an update group, this is exactly what we do. Right? You start with some guess. You look at the slope. If the slope is negative, you're gonna go right. So that means you're gonna add some number to it. Right? If x is if the slope is positive, then you want to go left. Is everyone clear though? Is everyone clear? Is everyone clear though? Is everyone clear? Any questions so far? If not, this thing is actually one of the most important equation in optimization. So essentially, you just figure out the next guess, right? So this thing is the basis of all the gradient descent. There are like 10 versions of it, but the basic is this guy. Okay, you want to walk in the right direction. Okay, you want to walk in the right direction with some step side. What is the sign of f prime x4 again? To figure out whether you should walk left or right. So for example, when you are at point A over here, your slope is negative, right? You want, then your x new is going to be xo plus some number, right? But if you're on the right, oops, if you're on the right, your slope is positive. Okay, you want to walk to the left. So that's why I do the minus. Right. I do the minus sign, and this is the direction. So it gives you the direction. Okay. Maybe you could call that. Even better, let's call Saran's fundamental theorem of optimization. There, there was a period when people keep putting their name on in front of the theorem. If you learn ODA, actually ODE and PDE, you're gonna learn a lot of special function that has a name. There is one period when people keep naming the solution to the differential equation no one knows how to solve. They don't even have the exact solution as well. There was a period like there's a guy named Airy function and so on. I don't know. You know what I'm talking about, right? If you learn ODE, the especially the nonlinear one. The nonlinear one, you cannot solve it analytically. So you just name the solution after yourself. How cool is that? Some other names stick though, like Airy function or Bessel function and so on. Okay. Any other question? Any other question? Let's implement this and see if it works. Okay. Let's implement this and see if it works. The idea is super simple, right? Find the derivative, which we know we learned it like week 2 or something. Find the derivative and then figure out which way you should go and then go that way for some fixed step size. Okay, let's do this. Let's do this. OBS and switch to full screen. And which screen do I switch to? I switch my laptop. Okay, good. I found a new browser called Brave. I like it a lot because it get rid of YouTube ads for me. I highly recommend. It's a Chrome. It's someone take Chrome and then implement it in a way such that YouTube ad doesn't work. YouTube start with no ads and then single ad and then 2 ads in between. It's just like, come on. Yes, it's better Chrome. Let me also, if you're interested, there is a JetBrains data spell. I think you guys can download the version. This thing is a really good, what's that called? A really good notebook environment as well. All the autocomplete works the way it should. Oh, please change it to Python 3. I forgot. Okay. So let's say if we try to, let me wait until everyone has the notebook, right? Let me wait 2 minutes. It's gonna take you a while to clone the notebooks and everything. In the meantime, let me eat some snacks. Nóng chính. Yeah. Okay, there's one application that doesn't respect do not disturb. Okay, so let's plot this. F of x, right, is x minus 2, and then square, and then minus 1. Oh, plus 1. Okay. And let's plot it from, minus 3, minus 4 to 4. Okay. So this is where we want, right? You can guess from the function itself that it has to be x equal to 2, but just as a pedagogical purpose, let's do this. Okay. So far so good. And we have our update rule already, and update rule gonna make it from 1.1. Okay. So let's write our gradient descent, right? Gradient descent, and you pass in the function you like, right? And the x0, you need the initial guess, and that's it. So I want you to try to do number 4 and see what you got. So let's write the gradient function. Okay, so let's do it. N. Okay, let's put n over here as well. For I in range n. Okay, fill in this. It's one line. Oops, and see if it does what you need. Give me back my desktop. Let's see if it does what you need. Right, guess and we guess. Okay, and maybe you need h as well, right? So you know how to take the derivative, right? So f prime is going to be f of x, guess, right? Plus h minus f, yes, minus h. We learned this, right? How to take the derivative like accurately. You use the midpoint and divide by 2h. So guess is going to be guess minus step side. Let me put in here as well, step side. Times f prime over absolute f prime. There's actually a function called sine, but doesn't matter. Let me print a guess as well. You'll see something. So it's the gradient of f, and then starting x0 is 4.0, and n is 10, and h, let's make it 0.0001, doesn't matter. Step size 1.1. For those of you who did that already, tell me, what did you see? Does it do what you need? Does it do what you thought it should do? Does it do what you think it should do? All is well. Let me push my code real quick. Okay, I pushed my code to the usual place. If you got this graph, let me know and tell me in the chat as well. Why aren't there 10 points? Right? You would expect it's going to be 10 points and you expect it to go to 2. Why doesn't it do what you want it to do? Okay, if you're done, raise your hand so I know that you're done. Yeah, if you got this graph, tell me as well why. We expect to see 10 points. Why do we see only 2? Anyone? If you got this graph, let me know. If you're done, please raise your hand so I know that you are done. You reach exactly the same point that I reach. It doesn't exactly do what we need, right? And someone help me. Uh, why do we see only 2 points but not 10? What happens? What exactly happens? They are the same point. Yes, if you look at this, if you look at the printout, right? If you look at the printout, it seems to oscillate between 2 points, right? It seems to oscillate between 2 points. Why is it oscillating? This is the question. It moves too far. It reached the minimum way too quickly. Not exactly that, okay? So if you think about it, what happened is the following, right? The algorithm tells the following. The algorithm do the following, right? It say that if you too far to the left, then go right by 1.1, right? If you too far on the right, then you go left by 1.1. So here's going to be what happens. So you start at 4. You go to the left, you get to this point, and then you found that, okay, the slope is still positive, right? You want to go to the left. How much do you go to the left? You go to the left 1.1. So you end up at 2.9, right? You end up at 2.9. And once you end up at 2.9, you figure out that, oh, wait, Ajahn, the slope is negative. Then now I should go back. How much you should go back? You should go back exactly the same amount that you walked in, right? You go back the same amount that you walked in. So that's why it's oscillate between these 2 points, right? So when you go back, you figure out, oh, wait, I'm like a bit too far. Then I'm going to go to the left 1.1, and this point going to say, I'm going to the right 1.1. So it's going to oscillate between these 2 points forever. Someone good, right? Here's the problem. That's the first problem. And a lot of you say, okay, Ajahn, that's easy. All I need to do, right, is to make sure that it oscillates, the length that oscillates, the distance between these two red points are exactly 1.1, right? So that means if you think about Ajahn, if I want the answer to be accurate, right, all I need is to make the step size small, because the length between the red points over here are exactly the step size that we put in, right? If we put in a smaller step size, maybe it's going to be better. Okay, so let's try that. Okay, let's try that. Okay, and this time I'm going to try for 100 times. Let's do n equals to 100. Okay. N equal to 100 and step size is 0.01. Okay, not bad, but you end up at 3. Think about this, you spend like 10 times more effort, right? Everyone got this graph, right? You with me so far, right? So there's sort of two contention, right? There's sort of two contention. You want the step size to be big because you want to reach the minimum fast, but you want the step size to be small to get an accurate answer. Okay, let me write that down. Everyone see the point, right? This is a very important point for you to understand the algorithm, why there are like some other correction that we need to do. Okay, if the step size is big, yes, you reach here in like 2 steps, but your answer is not gonna be not so accurate. But if your step size is small, if once you reach it there, yes, your answer is gonna be accurate, but it's gonna take you so many steps to reach there. Okay, so what we want to do is this. Okay, so the step size, let me actually copy here. Copy this guy. So the step size, okay, we want it to be small, give you accurate answer, but takes forever. If the step size is big, then it's gonna be a, what should I call, a rough answer, coarse answer, and then fast. Okay, everyone understand this trade-off, right? If the step size is big and the step size is small, okay, very good. If you want the best of both worlds, right? If you want the best of both worlds, we want it to be fast and accurate. This is what we want. We want it to be accurate and we want it to be fast. So Soran suggests one very important idea. So that means Ajahn, fixed step size is a stupid idea, right? If you think about it, fixed step size is a stupid idea because when you are here, you want to step really fast to the answer, and then you want it to be accurate only when you're close to the answer, right? Someone get, right? Then you're gonna reach it really fast, and then you're gonna be really accurate. Are we good? Right? So fixed step size is bad. It's terrible. Okay, so what we want to do is dynamic step size. Okay, and I think it's clear to everyone that when we are far away from the answer, we don't really need to be careful, right? We don't really need to be careful much, right? When we are far, so when we are far, we want the step size to be big. When we are near the answer, we want the step size to be small. Okay, so far so good. Which is kind of catch-22, right? Because you don't know where the minimum is. Kind of catch-22 because you don't know where the minimum is. So we should have a proxy of something. We should have something to tell how far we are without actually knowing the answer itself. Is everyone good with this concept though, that we want, when we are far away, we want the step size to be big, right? When we are far away, we want the step size to be big. But when we are close to the answer, we want the step size to be small. And we don't know where the answer is as well. So it kind of not knowing like how far, how near you are. But anyone has a good idea though. How do we mimic this behavior? How do we mimic this behavior? We want the step size when we are far away to be big. When we are near, we want it to be small. Anyone has a good idea? Anyone has a good idea? Can you tell how far you are from the answer? Ish, not exactly how far though, but can you calculate something that sort of tell you how far you are from the answer without having to know the answer itself? What do you notice though? Very good, Tanawin. The slope, right? The slope. Think about this. When you're far away, your slope is big. When you're close to the answer itself, the slope is like 0, right? Because that's kind of definition of minimum. The slope has to be 0. So that's a good. So that means what Tanawin said is very important. We want the step size. Let me change color. We want the step size. What happened to my pen? Step size to be, right? This thing is proportional to the slope. And let me put in the absolute because you want it to be positive, right? Are we good? This is a very important idea that Tanawin suggests. That if we want this behavior, the easy thing that we can do is that the step size should be proportional to the slope, some sort of function to the slope. Are we good? And the simplest one is just a constant times the slope, right? The simplest one is a constant times the absolute of the slope. Is everyone good on this? Any questions so far or any questions so far? This is the key idea on how to get it to work properly. Okay? So this happens all the time when you figure out, okay, this is my intuition. It should work. But then when you try, it doesn't work. Then you're going to go figure out why it doesn't work. And then you're going to fix your algorithm. Okay? This is much more important than like how many algorithms do you know, right? This is much more important. Knowing how to fix the algorithm is a very important skill. Okay, so let's do exactly that. So let me plug this thing in there and see what we got. Okay, so what we had earlier is xn plus 1 is xn minus step size multiplied by the slope over the absolute of the slope, right? But then Hanawin suggests that the step size should be proportional to the f prime. So I'm going to call it lambda f lambda times f prime x n, by the way, xn. Okay, and if I plug that in, you can see a whole bunch of magical things happen, like things cancel out. Xn minus lambda, oops, absolute f prime of xn multiplied by f prime xn over the absolute f prime of xn. What cancel out? What cancel out? The absolute term, right? You know you're doing it right if a whole bunch of things cancel. Especially in physics, if a whole bunch of things cancel, you're probably doing it right. Okay, so that means our new update rule, which is better as well, looks even simpler. It's only say xn plus 1 is xn minus lambda f prime of xn. Looks even simpler. And this lambda has a name. It's called the learning rate. That lambda has a name. It's called the learning rate. Okay, this is only one form of gradient descent though. Like I said, there are 10 other versions like on how they figure out the step size. Right? The version depends on how you figure out the step size and somewhat different in how you figure out the direction. In 1D, it's quite clear. In 2D, it's not quite clear. Okay, in 2D, you can play around with the direction as well. In 1D, it's quite clear. There's only left or right. Is everyone good? Everyone good? We're gonna go fix our thing with this. Okay, we're gonna go fix our thing with this. Is everyone clear? Right? The motivation is pretty clear, right? Because it didn't work. What is lambda? Lambda is called learning rate. It's some constant that you put in. And we're gonna learn the behavior. What if you put in too large and what happens if you put in too small? But at least it's better than last time, right? But at least it's better than last time. Okay, so let's go back to my thing. Green one. Okay, so let's try this. Let me fix this. Okay, let's call it the new gradient function. The gradient descent function, which looks even simpler. Right, so instead of this, we're gonna call it lambda, which lambda is reserved word in Python, by the way. So just call it LMB or something. Lambda LMD multiplied by f prime. That's all. And you need to put in the lambda, right? So instead of step size, you put in LMD. Yeah, and this thing is 0.1, right? Let's see what we got. Actually, let me put all myself to do what I want. Okay. So sort of do what I want, right? You know that the final answer is like two to like all intents and purposes. Yeah, typically lambda is small. Lambda is something less than 1. That's typically what happens. Typically, there's no real rule of thumb. Okay, the rule of thumb is less than 1, but there's no real scientific reason why it should be less than 1. Okay, is everyone good? Right, even better. But if you try lambda is 1.1, you're gonna see something weird. Blah, blah, blah. Aha, cool graph, right? A really cool graph. What's happened though? What happens? What happens? Yep, you overstep your solution, and because lambda here tell you to step back, but you overcorrect it by a lot, and then you overcorrect it by a lot, you overcorrect it by a lot more, and a lot more, and lot more. So you're gonna oscillate like this, but you're not gonna reach a solution, right? You start somewhere really near and then you get far away further you are. Okay, so if lambda is too big, it's not gonna work. Typically lambda is 0.1, 0.01, those kind of thing works. You can see it converts to 2 like really quickly as well. Right, it converts to 2 really quickly, and then the rest are just like, oh my god, it's like 9 digit after 0. That's good. And this technique is extremely powerful, right? So for example, the thing that you learned before midterm, the thing that you learn how to solve the equation, you can just do this, right? You can just do this. So for example, if you want x equal e to the x, that's easy, Ajahn. This is what I'm gonna do. If I want x equal to the x, right, I just change my f of x, right, my objective function to be return exp. Oh, let's put np.exp x minus x, and then square, and then square, right? And then I use exactly the same function, gradient. Actually, I just copy this. That works too. Just let me copy the one that works. Did I screw up something? What's the answer? Let me print the objective as well. Just a second. Let me fix this. So instead of print gas, print the objective. Print f of gas. That's better. See if that's the right thing. Why is it one? Maybe I start too far. Did I screw up something? Is that a local minimum? I think that's a local minimum. 0. Oh, my derivative was not that accurate. I think that's why. It's 1.7, right? If I remember the answer. No, should be 0. Why is it not 0? Okay, that's better. I think something funny with e to the x, like they probably never cross. Right, they never cross. Right, they never cross. So cosine x is x. So let me fix something. Okay. Okay. So that's better. Okay, e to the x and x never cross. Okay, so any questions or any question? Sorry about that, I digress a little bit, right? So you can use it to solve like x equal to cosine of x equal to e to the x, that the solution doesn't exist. The solution doesn't exist in real number, okay? So as long as you can formulate it, you can use exactly the same engine, right? This is the powerful. This is what makes the gradient descent really powerful. It's the same engine. As long as you phrase the questions right, you will get your answer. Okay. Well, if you think about this, okay, that's one thing that I want to note. Okay. That's one thing that I want to note. Okay. Let me put it here to let see here. What if your function looks like this? Okay. What if your function looks like this? This is your function. Okay. And you start here. What's going to happen though? What's going to happen? What's going to happen as you walk? What's going to happen? Right. It's going to reach, oops. It's going to reach this minimum, right? So this is one problem of gradient descent, right? This is where we want, this is the global minimum, right? This is the local minimum. Our method will stuck here. Will stuck here. This is the weakness of this method. It doesn't search globally, but this is kind of best we can do. Okay. This is kind of best we can do. Any question though? Any question? Yeah. Right. I want to tell you, this method is not does not guarantee to work, but it's very generic. Okay. Sometimes this thing is good enough for you, right? So for example, this is like your current business strategy, current. And this is the improved business strategy. Then if the gap here is, I don't know, $100 million, then that's good enough for me. But if you spend more effort, maybe you minus another 200 million. Yeah. So this is actually what the industry are using, right? When you try to minimize something, you do this. Okay. Any questions so far though? Any questions so far? Okay. So this does not guarantee to work. It's gonna get stuck at the local minimum. There are some methods that can prevent you from doing this, right? So for example, you can do the following. You can do the shotgun, right? You don't know where to start, so you're gonna start at many points, right? This is one way to fix it. You're gonna start at many points and let it roll, right? Some of them gonna roll here, some of them gonna roll to the wrong one. Then you pick the one that rolls to the right one. That's all, right? You just compare which one is less. So this is more practical approach on what people do to actually find the global minimum. They spray the initial point and hope that one of them gonna land on the better one. Okay. Any other questions so far though? Any other questions so far? Any other questions so far? Or everything is clear? Let's do something harder. Let's do something harder. Okay. This is like baby problem, right? Because you only have one parameter, Ajahn. Why do you need to do this? Good point. Right. You don't need to do this. If you only have one parameter, you can do something much smarter like plotting the graph. Yes, you saw the 3D graph. And wait a second, let me find the right one. Which one is the right one? This one is the right one. Okay. So next thing. Oh, sorry about that. Let me. Yes. Push. And let's do something better. The problem gets more interesting, right? If you have multiple dimension, which I'm gonna write in a fancy notation. Okay. So this is what we want to do. We want to do gradient descent, but in multi-dimension. Multiple dimension. Let's call it 2D. plus plus. Let me close this. It's lacking so badly. Okay, so in higher dimension. So this is the problem that we try to do. Okay, let me write my notation first, and then I'm gonna go back to your notebook. Okay, argmin. So remember that when we try to fit the graph, right? When we try to fit to do linear regression, we have two parameters, but you can have like 100 parameters. It doesn't matter. It's gonna be slow, but it doesn't matter, right? In principle, it works. Okay, so I'm gonna combine. I'm gonna call the multiple parameters, call it with x with a vector on top. Okay, it's an x with a vector on top, which means if you think about vector, it's just a whole bunch of numbers, right? It could be m and c, and maybe if you have a, b, d, whatever parameter is, just a whole bunch of numbers. My table. Okay, argmin of some function that takes in the position. Sounds good, right? This is what we want to solve. So the notation that I want to use from now is a vector notation, which, if you think about it, is just a whole bunch of numbers. It's just a compactified notation to make our life a bit easier. Okay. So this is the notation that we're going to be using. So let's get back to our notebook real quick, because I want to draw something for you so you can see. Not the notebook, the full screen. Yeah, let's go back to the notebook. Okay, so here's the thing. When you write it for the first time, the thing that you really want to do is to visualize it. Okay, you really want to visualize it. So let's do this. Okay, Matplotlib has a way to visualize this as a surface. This thing looks really cool, right? This thing looks really cool, except it's useless because you cannot interpret it, right? This thing looks really cool, right? The z-axis here is the value of the function, and the x-axis and the y-axis, I don't know which one is which, but one of them is x and the other one is y. Okay, you know that the minimum is somewhere around in the middle there, but you cannot really see it, what the x value and the y value, right? It looks pretty, but it looks terrible. So a better way to visualize this is to do something called contour plot. Okay, let's run this. And let's try to understand this. Okay, contour plot is the plot of the contour line. And the contour line is the following. It's the line where all the points in here, right? So this is the x and this is the y. And all the points, let's say on this red line, all the points on this red line, when you plug it into f of x, it's going to give you 200. Right? So you can see the trend, right? 400, 200, 100, and so on, and 10 and 2. Let me ask you, why do you think the minimum is? Why do you think the minimum is? It has to be here, right in the middle over here, right? Because if you think about it, this gradient descent is like you let the ball roll, right? This is a really high hill. It's gonna roll to the smallest one, so it's gonna be around here. And gradient descent is essentially rolling the ball. Are we good? Are we good? Okay, so contour plot, if you have two variable, do it. If you have three variable, you're on your own. You just trust that your algorithm works. It's so hard to visualize, but if you have two variable, yes, you can still do it. Are we good? Okay. So here's the thing. Now we have higher dimension. Let's go back to my notes. Go back to my notes. Okay. Now we have multiple dimension, right? Okay, and we have this ring over here. Actually, let me use technology. 2 seconds. Use technology because I can copy from my Mac to my iPad. Sorry about that. There. Lock before I moved it. Okay. We have our contour. Right? We have our contour. Let's use the color that I haven't used, which is purple, or maybe orange. Orange is good. Okay, so like before, right? Like before, we're gonna start somewhere. This is our initial guess. The goal is to keep improving this, right? The goal is to keep improving this. So you sort of want to walk something like this, right? You sort of want to do this. So that's good, right? So your update rule should look something along the following, right? X new x n plus 1 is x of n, right? Plus some sort of step size multiplied by the correct direction. And the direction is going to be some unit vector, right, in the right direction. That's good. So your new answer is going to be your old answer, except you're going to walk it to the right direction. And that's all there is. Okay. Anyone has a good idea what the direction is though? How to figure out the direction? Let me get your intuition first. You learn something from what's it called? Cal 3B, 3A. I don't know what the number is. The slope. Right. Last time we did the slope, right? Except the slope is only applied for 1D. What's the slope for 2D? Right. 1D that works clearly. It works. What's the slope for 2D? What did you learn in Cal 3? I don't know, 3A or 3B. Risky, tell me as a physicist, what is the slope in 2D? Multiple dimension. What is the slope? What is the slope really? Anyone tell me? Tangent something? Wait, you probably have this exam, right? If you learn Cal 3B. Rate of change. Yes, rate of change is derivative. But in higher dimension, what is the rate of change in higher dimension? Tangential plane. So close. So close. And you think too much. Okay. So I want to show that the direction that you should walk, right? So when it was 1D, it's the following, right? It's df by dx. Right? I claim the direction that you should walk is actually the gradient. You saw this thing before, right? The gradient of f. Okay. It's the derivative, except it's in 2D. So the definition, if you forgot, is df by dx x hat plus df by dy y hat. And Risky, you even know how to do this in polar coordinate and spherical coordinate, which I don't. Right. Let me show you why you should do this. But in your mind, it should work, right? In your mind. In your mind, it should work, right? Because if you draw the gradient for this graph, it's gonna look like this. Gradient looks like this. It's going from the lower, right? The gradient looks like this. So if you walk along minus of the gradient, right? If you walk along like minus of the slope, it should work, right? Gradient pointing out always. Looks like this. Are we good? Okay. So let me try to convince you mathematically as well on why you should do this. Okay. You should see this one in your life and then remember for the rest when they ask you again, you should remember this trick. Okay. So the reason goes back to like I said, everything in this class is Taylor series. Everything in this class is really Taylor series. So let's do this. Okay. So f, let's say it's a function of two variables. It doesn't matter how many variables, but you're gonna get the idea after you see two variables. Okay, even though I say discrete math, I'm proof by example, but I'm gonna do exactly that because I'm too lazy today. Okay, so let's imagine the following. You have the function of two variables, f of x plus y, but you're gonna move it a little bit. Let's call this thing delta x and move y by a little bit, delta y. Okay, let's imagine delta x and delta y is small enough. Is small enough. Okay. Tell me, Taylor series. You know, I know that you know only 1D, but guess. But guess what happens in 2D? The function right? The value of the function itself, when you move just a little bit from where you started with, what's it equal to? What's it equal to? The first term, what should I put here? What should I put here? The first term, what should I put here? What's your like zero order guess? Right? So for example, I asked you what is the function of 5.1, 5 plus 0.1, and 4 plus 0.2. What would be your guess? Can you tell me? What would be your first guess without the correction term? You guys learn about partial derivative, right? The root cause or the motivation of partial derivative actually come from this problem. Anyone? Anyone? Your first guess, your zero order guess for Taylor series, what is it? Let me write Taylor series in 1D. If you still remember, x plus delta x, what is it equal to? The thing is equal to f of x, right? Plus delta x, f prime of x. Exactly, right? So your first guess would be, okay, Ajahn, if you move just a little bit, your value should not change much from your first place. So this should be your first place, which is f of x and y. Okay? So that's a good, right? That's your first guess. Okay, now let's do it a little bit better. Let's do it a little bit better, right? Now we want to take into account the fact that you walk in X. What should I add? I want to take into account the fact that you walk in X. What should I add? Yes, very good. You should add the partial derivative, right? That's why it's a partial. This is important. It's a partial derivative with respect to X, right? At X and Y, and then multiply by how far you go, right? So this thing asks you if X changed by a little bit, X alone changed by a little bit. That's the definition of partial derivative. You change the X alone, how much would the value of the function change, right? And then multiply by the step size. Okay, everyone good, right? We take out X. What about Y? What about Y? What do we do? The same thing, right? Okay, that's good. Let me get rid of this. Delete. Any questions so far though? But of course, there are higher order terms, right? There's higher order term like delta. There's term that is delta x times delta y. There's delta x squared. There's delta y squared, and so on. But we're gonna ignore that. Let's ignore that. Okay, if delta x and delta y is small enough, then we're good. Okay, so we're gonna ignore that. Okay, now next question. Next question. Next question. Any questions so far though? The fact that I use the partial derivative, it's very important that we use the partial derivative because this thing only assume that x changes, what happens? This thing only assume that if y changes, what happens? The cross term, you know, is going to be smaller, right? It's going to be a lot smaller. Okay, so the next thing is, if you see this, if you see this term on the right, does it look like some sort of simple expression? Does it look like some sort of simple expression? What does it look like though? What does it look like? You multiply things element wise and then you add them together. What do we call it? For those of you who actually have exam on maybe next week on linear algebra, what does it look like? What does it look like? When you multiply like each, right? You multiply this, you multiply x with x, you multiply y with y. What is it called? And then you add them up. What is it called? What's it called, everyone? Okay, so let me just give it to you. It's the dot product. You remember the dot product, right? So it's a dot product between this okay, multiplied by dotted. This is actual dot product of delta x hat plus delta y hat. Okay, so that's good. I lump things up to r and delta r though, because you see later y, right? X and y becomes r. It's the same idea. Any questions so far though? Anyone see, right? It is a dot product. And this is the function itself, right? At the O point, plus the first term is the gradient of f. Okay. Dotted with the direction that you walk, right? This is the direction that you walk. And how far you walk. Is everyone good with this? Okay, so you can think about the left one. This is the new function value. Okay, this is the old function value. And this is the change in the function, how much you change, right? Think about this. You go is you control delta r, and then you hope that this guy is minimized. Okay, gradient of f, you cannot do anything with it. This is like fixed, right? Gradient of f, because if you are at some point r already, you are at some point r already, right? You want to see which way you should walk. We get, right? All these are delta r's. Everyone good so far though? 7 good so far. Okay, so that means now we know how much we're going to change the function only depends on the dot product between the gradient and the direction that you walk. But the gradient, you have no play on it because you are at the function is fixed for you and where you are is fixed for you. So let's say the gradient is here. So let me put the gradient here. Okay, the gradient is a blue one. Okay, the gradient is a blue one. Okay, so if let's say if we want the dot product to be minimum, how should I pick the direction for r though? For delta r. If we want the dot product to be minimum, like really, really small, how should I pick the direction for delta r? What did you learn in physics 1? Tell me. How do you get the dot product to be minimum? Even more than minimum, you want it to be negative, right? Because you want to decrease the function itself. Anyone? How would you pick it though? How would you pick it, right? Because you can pick it all around. You can pick it on any direction, but which direction would you pick so that the dot product is minimized? Do you still remember the dot product? The geometrical meaning of it? Perpendicular. Perpendicular give it a 0, right? Can you go negative? If two vectors are perpendicular, then you get a 0. Right. You want to walk in the opposite direction. Right? You want to walk in the opposite direction. So delta r should be opposite to gradient of f to minimize the function. Okay, if you go back to 1D, it's exactly the same idea. It's exactly the same idea. If you walk along the slope, right? If you walk along the slope or if you walk along the gradient, your value of the function can be increasing, right? If you're here and the slope say here and then you walk to the right, right? You're gonna be increasing your function itself. It doesn't help. So you want to walk in the opposite direction. Okay, and this is the key idea. Okay, this is the key idea. that the direction that you should pick should be the opposite to the gradient of f. Okay, so let's go back. Any questions so far though? Any questions so far? We're gonna come back and plug this back into what we know. Any questions so far though? Any questions so far? So the best direction is the opposite of f. Okay, the best direction is opposite of the gradient of f. Okay, which I trust you know how to compute gradient right by now. Not to reduce, to make it negative to the maximum, right? So you want to decrease it to the maximum. And it's not exactly the same plane. But you can think about it as the same plane if you want. Locally it's the same plane, but globally it's not the same plane, it's curved. But even within the same plane, you have direction to pick, right? Even within the same plane, you have direction to pick. You want to pick it in the direction of minus the gradient. Okay, so far so good. So let's come back here. So now we know the direction, right? The big question was the direction. We know the direction has to be the opposite of the gradient. So it's going to be minus of the gradient of f over the size of gradient of f. Now it looks familiar, right? You just change the derivative to gradient. So that's good. And the reason that I do this is so that I get a unit vector. That's all. I just want the direction. I don't want the magnitude. Okay. Is that one so far so good? Any questions so far? Or any questions so far? Okay. So the goal here is you walk in the opposite direction of the gradient. So let me put the minus over here. Okay. Any questions so far? Or any questions so far? Okay. I divide by the absolute because I only want the unit vector in that direction. Okay. Now, so far we know the following. Okay. But we should walk here. Okay. Any questions so far though? No question? Everything is clear? Okay. The code is like 3 lines though. You can write a really powerful code in 3 lines. That's so amazing. Okay, what about this? What about this? There is also another question of the step size. What do you want to do with it? What do you want to do with it? Anyone tell me? What do you want to do with it? And why? Do you want it to be big? Do you want it to be small? Or what do you want to do with it? Exactly. We want to do something like last time. We want the dynamic step size, right? So when we are far away, we are not afraid. Your step size could be as big as you like, but when you're close to the answer, you want it to be small. Otherwise, right? Otherwise, you're gonna keep stepping over the solution, right? If your step size is big, you're gonna keep stepping over the solution. Okay, so we want to do the dynamic step size, and we know we get close to the minimum if what happens, right? So we want the step size to be dynamic as well. We want it to be dynamic like last time. How should it scale? Can anyone tell me how should it scale? Last time it scaled with the derivative, the absolute of the derivative. This time, what do you want it to do? Right? The reason we want it to scale with the derivative is because we know when we are far away, the derivative is big. When we are close to the minimum, the derivative is small. So what should we do? What should we do this time when we have more than one dimension? Right. So you want it to scale with the absolute, the size of the gradient of f. Right? Because we know when it's near the minimum, the gradient, the size of gradient is 0. by definition, that's the minimum, right? When you're far away, the size of the vector gradient is going to be large. So this thing is going to be exactly like last time. Lambda, the learning rate, multiplied by how something that scale with how far you are from the answer. And you have the same cancellation. And the formula looks exactly the same. So the formula looks exactly the same, except you change the derivative to the gradient, that's all. And everything else is now a vector minus gradient. Actually, let me write the real thing. Xn plus 1 is xn minus the lambda times the gradient of f. Looks really cool, right? Looks exactly the same thing. Actually, 99% of the time, if you want to go to 1D to like multiple dimension, you change the derivative to the gradient and it just works. Okay, but changing the integral typically is requires some attention, whether it's a line integral or the area integral and so on. Okay, so far so good. So this is what we want to do. Any questions so far though? Any questions so far? Okay. Okay. If no question, let's go back to our notebook. Okay. And what I want you to do is to do number 8. Is to do number 8. Okay. And figure out where the minimum is. It's quite clear what from the picture, right? It should be around like 2.5 and I don't know, 1 or something. Okay. Please do number 8. I'll let you do it. Uh, Please do number 8. I'll let you do it. Okay, so wait, make it okay. Let me call it I instead of X because I want to use X. R and the function itself is this guy. Okay. Then you need to figure out the function to find the gradient, right? So, which is unfortunate. I caught one of them grab already. Gradient of f have some function r and h. So in x direction, let's make it two dimensions. Actually, doesn't matter. Should we make it more than two? No, you're gonna write on your own if you want more than two. You can actually make it more generic. So f of r plus. I think in the homework you need something more generic. What plus h times. I'm trying to make it like the least number of like. But let's do this. H is 0. Yes. Since it's a numpy vector, don't forget to copy it first. So for I in range n. Okay, you should have something like this. Okay, the code is push. This is what you should get, right? You can see the step size is large at the beginning and then it gets really, really small. What I teach you today is really a touch on the surface of gradient descent, though. It's actually, you can do a lot more. So for example, you can guess the step size much better than just lambda gradient. You can like interpolate, you can extrapolate it to a parabola and whatnot. Or you can do something smart, like, so you can see that this thing kind of curve to the minimum. What you want to do, you kind of want to go straight, right? That's a trick to make it go more straight as well. Okay, or even like at any point you can estimate the distance to minimum, like EDM and so on. There are a lot of things you can do, but typically the gist of it are exactly the same idea. You walk along gradient, the direction, and a whole bunch of things that you can calculate in between. Okay. If you got this graph, let me know by raise your hand though, so I know where you are. Because there are two more things I want to teach you. Okay. The problem that I show you is like a toy problem. It's a convex, so doesn't matter where you start. You can start at, I don't know, 15 and 15. 15 and 10. And what? It should be defined F. Right? 15 and 10 works too. You can see the step size clearly that gets large and then gets smaller over time. Yeah. So if you're done, then let me know by raising your hand. The code is push. Wait, no one's done or raising hand doesn't work. What happened? Oh, raising hand kind of work. So if you're done, please raise your hand so I know that I should go on. But you can see that this technique is really generic, right? As long as you have a function of many parameters that you can come up with, you throw it in here and it works. Ish, right? With a caveat, like with you may stuck in a local minimum, you may have like too large of the lambda and so on. Any question? You're done, let me know. Or you're doing something else, like and I cannot homework. Okay, I kind of want you to do it in class though, because typically there are some details that you may not see it until you implement it, so you can ask right away. There might be some detail that you ask, like, Dan, how do you take gradient and so on. But I think that's pretty obvious. Or you can try change something that you think it may or may not work. Right? So for example, you can try to change a lambda and see if it works or not. What happened to the rest? Are you stuck or you gave up on your life already? Any questions though? Like I only see two people raising the hand. Are the rest lost or what happened? So I can help. How to use NP the gradient. It means different things, I think. It doesn't mean what you want it to do. Right, it doesn't do what you want it to do. It's the gradient if you have the grid, if you have the grid array, if you compute every single point already, then that it computes you the gradient. Okay, what happened to the rest of you though? You lost or you copy and paste the code already? What happened? Okay. Anyhow, I need to go on. Otherwise, I will not finish what I want to teach you. Okay. So the code is push to GitHub though. The code is push. Okay. So you will see that at the beginning, right, you see that this method is so generic, and now you may ask yourself, Ajahn, why do we want to minimize? Why do we care about it, right? So let's look at this. The problem really about optimization is not exactly the algorithm to optimize it, because we have gradient descent. Every single function sort of work with gradient descent. Sometimes you do something smarter, but in general, gradient descent sort of works and it's actually used everywhere. Like on even on deep learning is essentially gradient descent. Okay, so the hard part of doing the optimization is never the optimization algorithm itself. No, not I would say rarely the optimization algorithm itself, but it's actually how to formulate your problem, your physical problem, into optimization problem. Okay, this is typically the hard part, and you're going to be tested on that. You're going to do homework on that. Homework going to ask you something very random. Okay, so you need to formulate it. I'm not going to ask you something like please minimize x minus 2 square for me. That I know that you can do it, but the formulation, it will take practice. So please do the homework. Okay, it'll take practice for you to translate the physical problem into optimization problem. Okay. So let's do the following. Let's look at the linear regression that we did last time, right? It's a very physical problem because it's clear that we want this line that pass through all the point, right? It's clear that we want this line that passes through all the point. Okay, we know we can use gradient descent. That means all we need to do is to figure out what is the objective function. Okay, if we know the objective function, if you write the objective function, then we are done, right? So for example, right, we want the following. We want to write f of r, right? That r should contain the slope and something, contain the slope and the intercept, and you want to minimize it. Right? You want to minimize it to find M and C. So this is what I want you to do. Okay, try write the objective function, right? You know from last time, it's a distance from the point to the line and so on. It's a distance from the point to the line, and I want you to minimize it to find R, which is M and C. Let me do this. M and C is R. Return something. Yeah, and then you're gonna minimize it, but you can use the gradient descent that you just used. Okay, please do this. If you know how to do this, then you understand it a lot more than phi M and C for me. Okay, And then if you plot on this, you're gonna see the line that you want it to do. Okay. No need to solve the matrix equation, but solving the matrix equation is much, much faster than this. This is slow. Could be some. Okay, as simple as that. This is all you need to do. And then let me figure out how to plot it. And then we do the gradient descent. Right? Descent. It's F R0. Okay, let's get it 0 and 0. Lambda 0.01 and M N, let's make it 100. And this is 0.01. And the X is not defined because I forgot to do this. Not close. I did something funny. Looks right. That looks right. Oh. Why is it? Oh, probably lambda is too large. It's found the minimum, it bounce back. Minimum, it bounce back. Okay, there you go. This is what you got. Let's make it run a little bit more. Okay, so we did what we did last time. So for this one, the objective is pretty obvious, right? The distance between the line and the point. And if it doesn't converge, try decreasing the number of lambda. Okay. Any questions so far? Or any questions so far? You guys are so quiet. Are you guys still here? So here's another thing. Here's another thing. In real life, you should not write your own gradient descent. In real life, you should not. There's a function for that. Okay. From scipy dot optimize, import minimize. There, and then what you should do, which is like 100 times faster because they write it in C and so on. Minimize the function, which is f, and give it the array. And the rest are like automatic 0 dot and 0 dot. Okay. Interest in on the picture. Okay, you can see you can get the identical line, and actually this one is a lot faster. So write this only once in your life, write your gradient descent, your own only once in your life, and then use the library for the rest. There are a whole bunch of other parameters. You can go read the doc. The important part that I want you to get from this class is actually how to formulate this. Okay, how to formulate the problem that you have into this objective function. Okay. Any questions so far though? Any questions so far? Any questions so far? Or it's simple enough, right? This thing is simple enough that you get the idea. But I want to show you that in real life, don't write your own gradient descent unless you have to. Unless you have to. Sometimes you have to. Use this. Just use this. There are like a whole bunch of other packages that does exactly the same thing, and every one of them is the function is called minimize. It's rare that you find the function called maximize. Okay, but you should not worry because you know by now that minimize and maximize are exactly the same thing. Okay, any questions so far? Any question? Okay, if no question, then let's do the harder one. Let's do the harder one. I think this one is pretty obvious. Okay, it's pretty obvious on how you would translate the physical thing that you want into the objective function. Okay, let's do something that is less obvious. Okay, let's do something that's less obvious. And this is actually the basis of machine learning. Okay, if you look at this, okay, everyone, if you look at this, you see there are two groups of data point, right? The red one, maybe the red the what should I call? The red one may be some let's say you want to classify a mushroom, right, by the weight and by the density and whatnot, right? And the red one is poisonous and the blue one is non-poisonous, is edible. So what you want to do is you want to find the separating line. So by eyes, right? By eyes, everyone can do this. By eyes, you just do this. You just draw the line in between, right? But it's going to be somewhat accurate or inaccurate depending on where you are. It's very subjective. Can we turn this, right? The problem of separating things into two groups, right? By a line. The thing on one side of the line, okay, is one group. The other side of the line is another group. Can we make this into an optimization problem? That's what we want to do. So I want a suggestion from you though. I want a suggestion from you. I want you to do this. There are like 10 million ways to do this. Just tell me one. Just tell me something. Okay. The problem is actually every single classification problem is this. The goal is to turn whatever your problem is into optimization problem and throw it to gradient descent and then you could be done. Okay. So let's go back to my iPad. Okay. So we have, this is the axis and we have the purple data point. Actually, it's the blue and the red. Red over here. Oops. Red. And maybe some other point over here. And the blue, which one point over here, and the rest of the point over there. By eyes, I think everyone knows, right? That we probably want to draw this line. Okay, but we want to turn it into objective function, right? So we want that line. That means we want to find M and C that does something special along the line of separating two groups. So this has to be arc, min, or max, doesn't matter. M and C of some function. And that's what we want to do. Okay, is everyone clear though? Is everyone clear? This is what we want to do. We want to find the objective function that help you draw the separating line. Okay. Any question? Any good idea though? Any good idea? Can someone tell me a good idea? Optimization of the average between two groups. Not a bad idea. Can you be more specific though? It's not a bad idea. But anyone else can suggest a new idea as well. Huh? You can suggest a new idea as well. Average between two groups. That's good. But can you be more specific though, Tanawin? Okay. But whatever we do, right? Whatever we do, we will need something along this line. We need to be able to tell whether something is above or below the line, right? Something is above or below the line. How do we do that though? How do we do that? Okay, we have M and C. We have M and C. I want to see if my data point, I don't know, X prime and Y prime, is it above or below the line? How do we check though that a point is below or above the line? Can someone help me though? How do we check that a point is above or below the line? Okay, now you start to need to use like all the things that you learned in high school and whatnot. How do you check though? What exactly do we mean by it is above the line? What exactly do we mean? Area of triangle. Which triangle? Which triangle though? We want to tell whether a point, like especially this point, how do we tell a computer that this guy is above the line? Okay, how do we know? Given M and C, given X prime and Y prime. Distance of what? Distance kind of do not have the sign, right? Distance kind of not have the line, right? Something really simple, something really simple. What exactly does it mean to be above the line? Exactly, very good, Van. Thank you. Right? Because y of the point is more than y of the line. That's all. Right? Right? Above means y point is greater than y line. Right? So that means we know y point, that's just y prime, greater than or equal to y of the line. Right? Which is m x prime plus c. Okay, so for this one, it's above. Okay, something as simple, and the reverse is true, right? If y prime is less than or equal to, let's make it strictly to make my life a little bit easier. Mx prime plus c, and this is below. Okay, what's next? We're not done yet, right? But at least we have a missing piece. This is always what you have, right? You want to translate the physical idea into something you can teach a computer how to do. Like now we can teach a computer, okay, now some point is above the line or below the line. Okay, so the next thing is we want to be able to score, right? So we want to be able to tell that green line is better than yellow line over here. Why is it? Why do we know that green line is better than yellow line? Why is it? More red points are incorrect. Okay, not bad, right? So we want all the red point to be below the line, right? All the blue point should be above the line. Okay, so let's look at this. So we want the red one, which I should write in red. We should want all the red one, all the red point should satisfy this. Y prime is greater than mx prime plus c, right? Wait, the other way, below, right? Below. And the blue, actually, it doesn't matter because you can flip M and C, you get another line. And the blue point, we want y prime to be greater than mx prime plus c. Is it above? We want that to happen. Okay, now, Tanawin suggests, okay, Ajan, is because more red point are incorrect. What about it though? So how should we score our line? How should we score our line? Remember, our goal is to write down the cost function, right? So the cost function should have something to do with what Tanawin just said. That the fact that more red point is on the correct more points are on incorrect side, it should call a bad line, right? So the score should have something to do with something like number of point or whatever, the fact that they are on the incorrect side. What do we do? Okay, we are almost there. We are almost there. Square the thing. What thing? Sharon, what thing? You actually close the. What thing? Square what? You have so many things. What do you want to square? You're close or you're close? Do you want to square everything? The y equals to mx plus c. Do you really want to square it though? When do you want to square it? This is a real question. Yes, you kind of want to square it. When do you want to square it? Right? So think about this. That f, right? That f, that's your score. Doesn't matter how you do it. So you should make it one way, right? You should make it, if it's high, that means bad. Okay. Typically high means bad. Right? And if it's low, it's good. Okay. So you can think of the function, right? That f over here, you can think of it as a penalty. Right? How we should penalize it when it does the wrong thing. Right? You can think about f as how we should penalize it when it does the wrong thing. Okay. So there are two questions. How, well, the first question is when do we want to penalize and how do we want to penalize? Two questions. When do we want to penalize a red point though? When do we want to penalize a red point? Right? If we sum over red, green, and blue point, then it's right. When it's on the wrong side, right? We want to penalize all these. Only if when it's on the wrong side. Okay, so let's look at this. Okay, let's think about this. So f, okay, we're gonna penalize on the wrong side only. So it should be some sort of sum of the point on the wrong side, right? At point on the wrong side. Okay, what's next? What's next? Okay, now we know if it's on the wrong side. So for example, if it's this line and red should not be here, this is wrong, and all these are right. So that means we are going to penalize only that point, not bad. Okay, so let me circle it. Okay, how much should we penalize it though? What do you think? right? So this line and that line, right? So we could penalize it like how far it is from the line, right? So that's good, right? So one thing we could do is like how far it is from the line. This is terrible. You're doing something better. You're moving on the right direction. But even better if you move across it, right? Then the red is gone, right? Then everything can be on the right side. Okay, because our gradient descent relies on gradient. We want it to be somewhat differentiable, right? We want it to be somewhat differentiable. If you only count, right? If you only count, let's think about this. If you only count the number of right and wrong, right? What's going to happen is that the green and the blue line, they are exactly equivalent and you have no idea which way you should go. Should I go left or should I go right? I don't know, right? But if you penalize it in such a way that it's somewhat continuous and it's somewhat differentiable to tell it how to go to the right side, then that's better, okay? So we are going to penalize on how far it is on the wrong side of the line. So that's exactly what Saran just said. Actually, let me do this. All right, only on the wrong side. Are we good? Right? And with only this, trust me, you're gonna get your line. Okay, you're gonna get your line with only this. As long as you don't start like too far off, right? There's some local minimum as well. As long as you don't start too far off, you're gonna get your line. Okay. Any questions so far though? I want you to implement this. It should be like, I don't know, 10 lines. And this is actually close to what is called SVM support vector, which support vector machine is close, but not quite. Support vector machine does something a bit smarter. But it gives you like sort of the same result in any way. Okay, so please do it. There's only one problem left, but I'm gonna let you do it. Only one problem left. I'll let you do it. And let me switch to the notebook. No, not notebook, full screen. There, let me get rid of this guy, make it smaller because you want this. Okay, so figure out how to write exactly this function. Then you're gonna be so proud. I'll let you do it. So you'll be so proud of yourself when you got this. At least you write your own machine learning. You can actually extend exactly the same idea to like much higher dimension as well with vector analysis. You guys are so quiet today though. What did Ajahn Kanat do to you though? Midterm or quiz or what? What did he do to you? The what are my data? The data are the color. Okay, so your data is in your D, right? So X and Y in D. Each point, right? If on the wrong side, score. Well, let's call it cost. Really, essentially, it's just this. Right? Go through the whole data point. Actually, I want to do this as well. Let me do this. And the color. So I can do this. Step the and what did they call it? They call it C. Bad naming, but good enough. Oh, I use C over here. Do this. And wait, what happens to my point? Aha. We can, and there. So now you're equipped with the tool that can solve every single problem there is in the world. But there's some trick that you need to do though. So you can essentially solve it, but sometimes it's gonna take forever. Support is push. Okay. You can see a very simple idea, right? That we can build from physical understanding of the problem. This is the most important skill I want you to get from this class is how to transform some physical problem into something you can throw it at a computer or throw it at a library and get it to solve. Okay. This is like the programmer that brags about how many languages they know. No, no, no. If you know one, you know them all. But right. So the formulation is much, much more important than knowing how to use a library. How to use a library is important as well, but the formulation is important. Not the evolution of universe. There are people who actually do the simulation though, putting all the physics, and then it gets more complicated because like I said in discrete math class, right? We know like two bodies problem that's solved. Three body problem is unsolved for like hundreds of years. And then we have the question about four body problem and so on. Like I said, you can solve it, but it may take forever. Any questions so far though? For those of you who are done, you may go though. I'll stay here for a while. Okay. And as a reminder, the homework, please do it. Please do it. The homework, please do it before midterm because homework 1 to 4, I'm gonna get the TA to grade it during the midterm period. I don't see much of the Mario though. I see Vans one, which is really cool. I actually don't have the solution to them though. You can find it from the previous batch if you want. I probably have them somewhere. Problem 6, what is it asking though, man? The peak, right? Was it the peak? The peak fighting, right? Okay, let me give you a hint. If you got that far, then you should be fine. Don't worry too much. Where is that? Let me give you the hint. Okay. So there are many ways to do it. There are many ways to do it. Some people do it in a not so good way. Let me tell you the cool way to do it. Okay. So you have a noisy peak, right? Maybe this guy as well. What you want to do, man, is to fit a parabola. A parabola we know, right? Ax squared plus bx plus c is equal to 0 or something. Oh, equals to 5. Right. So maybe you can scan for each 10 points. Right, and fit the parabola. And given the parabola, you can check a whole bunch of things, right? So for example, you can check whether it's curved up or curved down. Right? If it's curved down, then you can ignore it if you want. Right? Right? You can do the rolling window and whatnot. Right? If it curved down, then okay, you can ignore it if you like. If it curved up, then okay, maybe you start questioning because there are many ways for you to curve up, right? You can curve up like this as well. You start questioning that you can curve up. There are many ways to curve up, right? But if it curve up, right, given A, B, and C, you know where the peak should be, right? The peak should be like minus, you differentiate it, set it equal to 0. I think it's minus 2b over A or something. 2a over b or b over 2a, minus b over 2a, right? This is the y max. You could check whether the peak that you expect to find is within the range. So for example, this guy, you expect to find a peak outside the range, right? You expect to find the peak. You expect to find the peak. So for this red range, right, you expect to find the peak here. So you can ignore this as well for that reason. Okay. But for the green one, you expect to find a peak. Okay, maybe within your range, then you just use that as your Y max. This is what I would do, but there are like other ways as well. You can mix and match if you like. Does that help? So essentially fit the parabola and look at the parameters and you should be able to find something about it. That's one way to do it. Some people fit like polynomial to the 7 degree. That sort of works too if you want. There are some other funny some other funny solution as well. Doesn't matter what you do, as long as it's good attempt, then I'm fine. This is the problem where I see a lot of smart students get stuck because they think too much. Not think too much, think like computer. I can tell you where this guy get used. This guy get used here. So if you do chemistry lab, sometimes you try to see the spectrum, which wavelength it absorbs. You're gonna see a lot of peaks, and then you can identify the element based on where it peaks. This is lambda, or maybe the frequency. I don't know which one is which. Let's say the lambda and the intensity, right? I think risky see it in if you take astro or and whatnot, right? You look at the star and you see, okay, which peak it absorbs the most, and you kind of figure out what the element of the star is. Then you need a computer to find these peaks where they are. This is why it get used. It get used a lot of application. You need to find a peak. Okay. Most of the thing you see in this class is very practical, though. You may think it's abstract, but in the homework, I show you where it get a real practical use. Okay, so even the is it Apple or Mango? I don't remember. Apple problem, right? That how much supply should buy the Apple. That actually business optimization, right? Figuring out the supply and demand. Like if you are a buffet shop, right? How much you should stock your meat. Okay, so that actually save a lot of money, and you charge people a lot for the money that you save them. So maybe they don't save the money anymore. What we learned today, like let me emphasize, is extremely powerful. As long as you can turn your problem into optimization problem. Yeah, it's extremely powerful. If no question, you may go now. That's all I want to teach you today about optimization. Next time, I don't remember what we're gonna learn. Any other question? If not, we're gonna call it a day. Any question? Okay. So see you next week. Bye everyone.